So what we'll do today, and this may help some. It really depends on where you are in your project. Is I had offered to do some live debugging of a couple of projects today, and a couple teams did take me up on that offer. And if this goes well, if we decide that this was a worthwhile use of our time today, we can do it again on Friday and potentially even next Monday. It depends on the nature of the bugs and how far along you are with things. Obviously, if you just have code that doesn't compile, I can still help with that, but that's not really a debugging skill. That's just understanding the syntax and making sure your files are in the right place and things like that. Um, w- I think it's not the value in solving the particular bugs that these two teams who were brave enough to kind of send there and share their code. I don't think it's the bugs themselves that matter. I think it's more about the process, and it's a process we could follow for all sorts of things that we want to debug. But I guess it's a fairly specific process to debugging using this testing framework for a MIPS single cycle processor. That I can't say that there's one exact correct way to do it. What I'll just do is just kind of share, and it'll be a little bit of a stream of consciousness. I have not resolved these bugs yet, so this will be live. Um, just a stream of consciousness about how I would think about the problem, how I'd work backwards to a solution, and hopefully that'll be somewhat useful for you as you're going through that same problem. I have not yet seen in this course in total a bug that was more than a 5 minute bug. It's a question of whose 5 minute and 5 minutes and which 5 minutes. But they're almost all those kind of 5 minute bugs with what we're doing here, and you're going to have a number of them though. So you have to get it down to 5 minutes. If a bug that's a 5 minute bug for the TA or for me is a 5 hour bug for you, that's where you're going to really struggle to finish this up. So hopefully this process will help at least a little bit with regards to how you're going to debug stuff. So I'm going to connect to the VDI here if I can. It's always a little laggy for me. And let's see if I can show you my screen on the VDI. Okay, so everyone should be able to see that. The nice thing is, even if in this live stream, if things are a little low resolution and you can't see all the waveforms and everything you'd want to be able to see, I am recording it. I have looked back and replayed the recordings of things like capturing this remote VDI, and model sim and all of that, and it's pretty viewable. So even if live things are a little blurry, you can go back, and I will always be posting the videos for these, assuming I am properly recording this, and you can take a look at what it is after the fact. So I have one of them preloaded. I don't think either member of the team is here today, so that's fine. They didn't want to. I wasn't going to say who their name was anyway, but they'll have to watch the video offline if they want to figure out what was wrong with their code. Um, so first off, the first part would be, when you're going to double click that batch file and you're going to run a test. This test isn't too big of a commitment, but as you start working on more and more complex designs for your embedded systems, um, as you start working on more and more complex designs for your embedded systems, uh, the time it takes to actually run a test is going to be pretty significant, especially if it's a post synthesis test as well, which we're not doing in this course, but in general, you'll be doing a lot of. And so the first part of the debugging process is, what do I want to test here? What am I even trying? Why did I click that button? What am I hoping to accomplish? That may sound trivial, that may sound obvious, but I think it's very important. It's I have something. Of course, the first time you try, you're just trying to see what blows up. I understand that. That's fine. But otherwise, once you're in that debugging process where you're trying to get past the problems that you're facing, it's okay. I've clicked that file. I'm going to load some assembly code here. What am I hoping to accomplish? What am I going to be looking for? So that it's not just kind of a blind guess. It's not just digging into 1,000 signals and 1,000 clock cycles and trying to figure out something might not be right. That takes time and experience to get good at, in terms of knowing exactly what to look for. As you get more comfortable with the design, it'll actually get easier and not harder for you this semester. But I think that's always pretty important. You have to be deliberate with what you're trying to test. Fortunately, I think that assembly code for the add-I sequential test is a pretty good one. It's simple enough. It's testing a small enough subset of the MIPS functionality that it is a pretty good starter test for us. We could do a simpler one, but this one's probably good enough to get started. It should tell us something. The log file doesn't tell us all that much, but at least tells us, based on the test bench, Okay. Does stuff compile? That's important. It compiles. Does it run? I do hope that this does compile. Um, does it simulate? When it simulates now, as we do that line by line comparison of just the Mars log output and the test bench logged output, what is wrong? What is different? And it's a straight diff of just the writes to the register file and the writes to memory, and are they the same or not? That's all it's basically doing. And there's a lot of windows popping up here, but let's before we even look at the model sim window here, you should be able to see this. This is our command prompt window here, and actually already does tell me a lot. You should probably have the assembly file open as well as you're doing this test, but we all probably now know this initial assembly code well enough to know what it's trying to do, right? It's initializing one in register one and two in register two, et cetera, et cetera. And those are the writes to the register file that it should be expecting. So for that first instruction, I don't like how it says, "Oh no." Okay, I didn't write that code. Oh no, something's wrong. But fine. Okay, it found something that's wrong, and it's starting with that first instruction number. The word cycle here is a little misleading. It's not a cycle in terms of necessarily clock cycles in your model sim waveform. It's just referring to updates, activities in our log is what it's referring to as cycles here. So you can't directly correlate that to clock cycle number one in your model sim. But it is saying that the add-I instruction, which should be writing the value of one to register one, that is correct. The student is writing register write to register three, a value of three. And I look at that and I say, well, that's a good sign to me in terms of the type of bug we're looking for. That means you've done a lot right, first off, right? Because you're writing something to the register file, and the test bench is catching that and it's logging it. And we do eventually want to write the value 3 to register 3. So something very simple is wrong. Very likely, I would say here. Um, your data path is working. Something's not getting logged the way we would expect it to. That's all that I'm seeing here. Because even later on, it is a little weird that it's off by 2 like that. It's off by 2 here, and it's off by 3, and then it's off by 4. That's a little that's that's a little unusual, but it looks like it's doing the correct operations. Maybe it's just not logging those instructions that are happening, beforehand. If otherwise you were getting, student is writing XXX to XXXXX, we see that a lot. That's usually a sign that things just aren't even hooked up right, and we go back to the diagram at that point. For this one, because it does look like things are generally hooked up correctly, we just have some logic bug somewhere in our design. And then we would want to look at the waveform at that point to see, okay, why are we writing to register three, or why does it think we're writing to register three and ignoring the initial writes to register one and to register two? And so that's why the script nowadays does pop open model sim directly for us. Opinions differ as to what is the right amount of signals to look at in your waveform. I agree with the argument that too many can be overwhelming. Right, there's just and it can be slow too, but too many can be overwhelming when you have all that, and that's what I do by default. Okay, I'll add all the signals. I can always ignore the ones I'm not interested in. Um, this is okay because the simulation already happened, and we're just opening up the log file. If you're running the simulation live, that would be the next step. Okay, I have a bug. What signals do I want to capture to be able to look for what could potentially be happening? For this design, we're talking just a few hundred signals at this phase of your design. Um, all of them is probably still tractable. The hardest part is really at that point then deciding, how do I really see it all on one screen to see what I want to see here? Um, what can be helpful? It's very much a hidden option there. I'm selecting toggle leaf names and full names because these full names are fine, but you have to kind of move the window all around the place to see. So I just toggled leaf names. So that's just not the full hierarchical name, which can be relevant information, but everything's really happening at that one level in this design. Presumably your adder is working and things like that. So we're looking at that one level of the MIPS processor. So from that perspective, looking at the leaf names, just the actual signal declared names, is fine. Um, I would also say this is a separate issue, and it wasn't as important at the time. But something else I did notice is that model sim simulation did take a while. Um, So and based on the fact that this simulation appears to still be going until it probably times out, my guess would be that halting condition is not being implemented quite correctly yet. That's necessary, but that's not that big of a deal either. It just means your simulations will be that much slower for every test because it runs for a certain amount of time and then it just gives up. Is what we've seen. And for some who are working on the more complex code, like the N Queens example, which I said was a slightly evil piece of code, you do have to increase that timeout because it just takes a long time to simulate. That depends on the speed of the machine and the VM and all that. So I can't say exactly how long it takes in terms of real time, but it takes more than 30 seconds in real time to run that code. So this one's timing out. We should fix that. We don't need to fix that yet. It's not that big of a deal. Um, a very common bug, which I don't think would be the case for this one because it is doing stuff, is that it's not coming out of reset properly. Would be a common problem with your code at this point. I think the reason for that is often because, for previous labs where you were both creating the module and creating the test bench, you had a lot of wiggle room with, how you were resetting and initializing the design, and you were kind of co-designing both the code and the test bench. Well, here the test bench is fixed, so you're not modifying it at all, right? And so you have to obey what the test bench is doing in terms of clocking and in terms of reset, and that could be a cause of bugs. That's a common thing I like to look at. Um, but we do know, again, going back to that window here, that we are getting instructions that are loading, and then we're just logging this write to register 3. So I would zoom in a little bit here. Um, there's ways using this little icon here to kind of select a region and zoom to a region. I can't get that to work right on this VDI box for whatever reason. Um, but we're looking at just a few clock cycles here. I don't know. Now we're going to enter stream of consciousness phase here. So this is our reset. There should be nothing particularly interesting happening while we're resetting. That first instruction writing values to the register file should be happening here. We've had a reset, and it is an asynchronous reset here. And then we have our first instruction that's kind of happening here. Read, 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 do work, do work, do work, write to our first result, and update our program counter and all that at that point. And when we look at that, just based on the names of the signals that we know are most relevant for us here, um, let's make it purple. That doesn't look any better on your screen. Fine. We do see that it is doing what it claims it was doing. Right? There's no magic there. Both the right address and the right data for that first write that the test bench would be logging, and I assume sreg write is also 1. It's 1 throughout, which is going to cause a problem at some point. But it is writing the value of 3 to register 3. That's a good place to be. The framework told us there was a bug. We have now found exactly where that bug is. I don't know what's happening yet, but we found exactly where that bug is happening. That's a good place to be. And I don't know if there's a magic process that follows other than just kind of working backwards from there. And I work backwards from there, and I say that doesn't seem right. We should be on our very first instruction at that point. So I would have to go backwards in terms of looking in time here and say, why are we on our third instruction? In fact, the actual instruction is here. I had told you in the beginning of the semester and no one believed me, but I bet a lot of you know exactly what that instruction is just by looking at the hex, 200, 303 as an add immediate to register 3, the value of 3, right? So that it is on the third instruction already, and it's not supposed to be. It's supposed to be on the first instruction at that point. So our program counter must be wrong. Our program counter is also on the third. PC equals 8. You'll need to initialize your program counter differently eventually, but that's okay. For now, this won't detect it as a bug. So I look at this and I say, this processor is correct. Something's wrong with your PC logic. Why are we on the third instruction already? We should just still be on the first instruction as we come out of reset. This is weird. It's good weird. It's good weird. Obviously, if things were working, you wouldn't need me. This is weird though. right? These transitions that are happening here, right, where it goes from PC equals 4 to PC equals 8. It looks kind of correct because like you're seeing like these pulses happening at these equal intervals, but um, but that's weird, right? Because it's happening like in the middle of a clock cycle. That should not happen, right? So this is half a clock cycle. This is like a third of a clock cycle. This is again, so it's updating every other clock cycle, or it's updating twice per clock cycle. Um, and we can work again. That's working backwards from there. We're seeing that that third instruction is being executed when I would expect it to be the first instruction. We see that the program fetch instruction fetch logic seems correct because that's the third program counter is fetching the third instruction in our instruction stream. So to me, I look at this and say my program counter is wrong. Why am I on my third instruction? Why is PC equal 8? Should be equal 0 still at this point where we're at that first valid write that's being logged here. Um, and well, there's really not that much else to do other than to dive into the code at that point, and look for something corresponding to our program counter, which you are supposed to use that next instruction address field. It's supposed to be able to copy paste that for me, and it did not. Okay, so just seeing where else this is being used in the code. That's fine. You don't touch that part where we're actually interfacing it to the instruction memory. Um, and I'm going to say it again. You know, the team that's brave enough to share their bug with me today, the code looks really good. I don't know. At first glance, everything looks right. You know, so this is a fun one. Register n bits. That's from like lab number 3, right? N bit register with the clock reset. Write enable is 1 is okay for now. For single cycle processor, that's okay for now. The input data we want to the input data we want to fetch. I don't know what happened there. Is I broke something. Is PC something called PC plus 4, which at least sounds correct. You know, just because the signal sounds correct doesn't mean it's correct, but it did sound correct of PC plus 4 out. And we saw we were getting plus 4. Everything was looking good, right? Because we were seeing those plus 4 operations happening there. Where is that adder? Let's find that just to make sure. Okay. Well, we're not going to edit this directly in ModelSim because ModelSim stinks for editing files. So we have the code here, and we will just directly edit that in our favorite alternative editor of Notepad++. I don't know what was happening there. Was it called PC plus 4? There's PC plus 4. Got your full adder. I look at. I'm guessing it's working, right? That looks correct to me, right? Take the current PC with an adder, add 4 to it. Ignore the cout. That's what you can just tie it to open if you don't want to use it at all. And you have your PC plus 4 out. But when we go back to the waveform, we are getting the plus 4, but it's happening at weird times. So register's broken, right? That would be my guess. Why is that register updating in like the middle of a clock cycle? The reason I am a little slower to say that that's obviously the case is presumably if your register is broken, which you're using, you know, in the register file and you're using the program counter, there would be there'd be a lot of things broken if it was just the if the register was broken, you'd see a lot of errors. Whereas this design is extremely close, and I gave you this file too, right? So well, you made an n-bit version of the file that I gave you for this back in lab number 3 or whatever it was. So there should, if there's a bug in here, it's my bug, right? It's got my name on it, or no, it does. Oh, you took my name off it, so that's a bad sign, right? So okay, so that's where the bugs come in play, obviously. Um, Clock reset, write enable, DQ, fancy data flow to implement the write enable, process with clock and reset. Okay, right? So that's our sensitivity list. So that logic triggers when either the clock or the reset changes. When either the clock or the reset changes, it's triggering that logic, and you're getting those funky latch behavior that on both sides of the cycle. both sides of the cycle, it's updating that register. So that is not a register. That is a fun, wacky SR latch thingy, right? For it to be a register, we would want to only write the value on the rising edge of the clock. I don't know how this. I mean, it's very cool that this design worked otherwise, but that was not a register. So, um, if it's so that's an asynchronous reset on this register, which should work. So if it's reset, reset. Otherwise, only on the rising edge of the clock do we actually want to latch that value. That's what makes this a flip flop versus a latch. Um, cool. I'm sure. Well, and okay. So, and I would say that's a good philosophy to follow, though. Okay, we have, I think, probably fixed a bug. Probably. I can't say definitively. I would focus on fixing one bug at a time. Don't try to fix 10 things. When you fix 10 things and it still doesn't work, well, okay, which of those 10 things was correct? Which of those 10 things made it worse? It's hard to isolate how your changes are impacting what your design is trying to do. Let's try it again. It's going to run a while because I'm guessing that halting thing is still not working correctly. That's a separate, not super duper important issue. I don't know if you can see that. That is victory. So okay, that was it. And if we look at the waveform for it again, yes, model sim being model sim. And it actually did terminate correctly here. So that even that part was correct. There we go. Now you're seeing those updates happening like on each clock cycle as it should be. Um, so at least for that test bench, for that assembly code, this processor is now working correctly. Um, Yay. Okay. Well, that did take more than 5 minutes. I was going slowly, trying to explain my thought process, but that did take more than 5 minutes. Um, let's take a brief break with our debug parting, and let's have our quiz party, which is as fun as the debug party. So I will set up the next one while we take that quiz. So if everyone can open up Canvas here, we are on that quiz number 9. If you describe it as a party, um, it's a good time. And you should be able to open that up. It should be valid. And I'll type in the code in the chat here. IH8. And let's take about 5 minutes and give that a go here. Um, this should look very familiar. It's just a canvassy way of doing it with regards to the data dependency exercise we did in class on Monday. Let's take about 5 minutes. Take just a couple more minutes on this here. Again, you're matching the producing instruction on the left with the consuming instruction on the right. So first instruction is producing a value of 9. So the question is just asking what are the instructions that are consuming that value of 9. It's easier, I guess, if we circle and draw the arrows, but I can't do that in Canvas. So you have to kind of just select down. Quiz party isn't nearly as jovial as the debug party. We're doing our best though. Almost done here. Let's give you just one more minute. All right, so you can continue to finish that up if you need more time, but otherwise, I think the rest of us we should move on. Let's do um, one more example here of a debugging session. I think the challenge is we could probably spend every day, all day on this, and it's maybe not overall the best use of our time. But I think as a couple examples, I think it's worthwhile. We can do more on Friday as well. We have to cover our content as well in this course. I'm glad people are liking the quizzes. I mean, I don't know. They are hard to put together, and every time it's, for example, on the exam, I think I've put together a great question. I realize there's a lot of ambiguity, and it's not really that clear what the right answer is. So harder than it looks, um, and within the limitations of doing it in Canvas. So this is the second group, and I want to again reiterate. I appreciate it. It takes some guts to come forward and say, "Hey, I need help on this. Help me out," and I'm happy to do so. You are staying relatively anonymous. If accidentally your name comes out in the source code, that's fine. We are all rooting for you, as a class here. Um, first off, it gets a warning when I just ran the batch file that the test bench has been modified. It's possible that that just happens due to opening it up in a different text editor that maybe has different tabbing and spacing or something, or even just line endings or something like that in character encodings. Doesn't mean you've changed it, but definitely if you get that warning, confirm that you haven't changed the test bench, only because that makes it not something that our TAs can then test because they're going to be using our version of the test bench for that. Could be you've done nothing, and that's just something to do with character encodings and nothing you've done wrong. Okay, so same process. I think that add-I test bench is simple enough for us to figure out what's going on. Again, as you get to more subtle bugs later on in this project, you may need to be making your own test cases, right? And I may ask you to do that, versus saying, well, on line 78, our code is failing. I think instead it would be better. Well, I've reproduced the bug using just these three instructions. Help me figure out what's happening with these three instructions. I didn't look at what the message was saying there, other than it was not happy. It was saying, "Oh no, oh no," and this is going to be a common place that a lot of you will be, which is, this is what Mars is supposed to be doing, writing to one to register one, and it's logging something for you, but looks pretty unhappy about that. 0000000x. Um, I believe the technical term for this bug is stuff not hooked up right, and we got still have to figure out what that stuff is and why it's not hooked up right. Um, but if that's the most likely case, if you're seeing that. And the trick can be that there's more than one thing that could be not hooked up right. It could be your processor is actually just fine. And you may find this that if you look at the waveform, as we'll look up in a second here, yeah, things are doing what they're doing. Look at the values in the register file, they're getting updated. Well, that test bench, when you look at it, is looking for very specific signal names for its logging purposes. I can't divine your intent in terms of what you're calling your write enable port on the register file. I give you a signal called s underscore reg write, and that's what you have to use. That's what it's logging. So you have to wind up using that signal. For the write enable, that's usually not as much of an issue. But for example, the write address, as we add these muxes, right? As we have our register destination mux, I think the temptation is to take that signal that you've already figured out, register destination. As you add a mux to it, the output signal now has a new name, new register destination or something you would call that signal. That won't work with the framework. That's a very natural way to update your design as you realize that that mux is now needed. But for the framework, that final signal, that's actually the address port on the register file that's getting mapped to the address port on the register file, has got to be called by that specific name. So I mentioned it in the channel earlier as kind of working backwards from how you would normally do it. You just have to preserve those very few signal names. And that may require kind of reordering what is the input to my mux, what is the output to my mux. It's all just labels in a diagram, but for this test bench to work correctly, those labels have to be very specific for it to work. So that could be the case. And we can determine that pretty quickly by looking at ModelSim and figuring out, is ModelSim just generally unhappy with what it's seeing here? Or is it actually happy and it's just a little artifact of how we're doing our testing? And we can zoom in a bit here, but there may not be a need to yet for this one. Um, I would refer to that as our stuff not hooked up right condition here, most likely, right? Just like with other stuff you've been doing. When I get a lot of X's everywhere, it is a little interesting that it's a lot of zeros and then only an X in the least significant little nibble there. Um, so that's maybe something with the ALU, but it's still kind of garbage in, garbage out anyway, right? Um, that doesn't tell you what's wrong, but there are those basic signals we want to look at, right? We have the program counter value, and I had mentioned that first instruction should be executing and finishing right around here, right? That uh, first rising edge after we've come out of reset should be that PC plus 4, and that's PC plus X, right? Is what we're seeing here, and actually, this signal does look correct, right? So we are loading that instruction that we're expecting. That's our add immediate of 101. Um, but then I think otherwise there's no surprise that it's all kind of something's not hooked up with regards to that instruction would be my guess. Could be a lot of things. It could be too many things, I guess. I don't think there's an obvious thing that it could be other than stuff not hooked up right. So let's take a look at it. This may be more than what we can resolve today together, uh, because you do have to basically have stuff hooked up right. I know that's a little circular, but you at least have some basic things hooked up right to start really testing this, and that's the truth of it. The framework is only helpful once you have a basic data path that is generally wired together correctly. Otherwise, you're just going to get this. Um, I mean, just guessing, right? Because you do have a lot of signals that seem appropriate, right? You have some internal signal referring to your instruction, but that one's all X's, and all this other stuff is X's. That's what I would look at next. You have your component block. You have the actual uh, instruction value here. That again, you're not touching any of that. Um, we got some signal flipping going on, which is always good to see. Um, but that's commented out. So we have all these instruction fields, and that would be the first thing that's not hooked up. So that would be the first thing to implement is to make sure, whereas you're using this instruction signal, so you still have to hook it up. I don't know. We can try it. That instruction signal that you have, and you can call it internally. You can label it whatever you want to make your life easier. But we have to use the signals that are already wired up to start with. So you have some instruction in your design that you're wanting to do your operations on, and we have to wire that up. That has to be connected to what's coming out of our instruction memory. Because again, if we look at our waveform, that value that's coming out of our instruction memory is correct. At least we know that that's what our first instruction in the instruction memory is. But then all your other stuff is disconnected. So it's unlikely this is going to magically work once we've made this change. But again, that's my philosophy of one bug at a time, or one class of bugs at a time. I think is a good approach to take. Um, it'll take more than the time we have in class today to maybe hook this up entirely correctly. But that would be the first place where it's not being hooked up correctly, and we can then go from there. Compiled, simulating, those are all good signs. Um, there's no way this magically works with that one line change. I mean, at some point, you have to determine what your level of hope is as well when you're running this test. Like, what is your percentage belief that things are actually going to be correct here? But that was significantly more promising, right? It went by very quickly. But if we go back to what's happening in our error window here, in our console window here, um, again, our first instruction is writing the value of 1 to register 1, and what we have logged instead is writing the value of 0 to register 1. Well, that's a really good sign to me. And likewise, our decoding of instructions, at least some of that decoding of instructions, is correct. We have we're triggering the correct writes as they're happening, so we're using that reg write signal correctly. We just have the wrong value, and that's fine. We just now have to work backwards from that value. We could probably look at the source code to see that, but I think also since we have this open, there we go. We should be able to look at the signals one more time. Reg write data looks a little unhappy, and that is a signal that we are logging here. Let's zoom in a little bit because again, I think really you just want to fix the first bug that comes up. Those bugs certainly in our assembly code compound, on each other, and so we can really only fix one at a time. I think in general, but our program counter and all that looks really good. Now that our instruction is hooked up, that also looks good here. Um, there's a lot going on. Reg write data does appear to be wrong. So that's again, this is our first edge, and keeping that cursor there is probably pretty useful. That's our first write to the register file, roughly here, and we are writing 0. So the framework is reporting back what we are actually seeing here. So there's no shock in place there. I don't think without knowing more about this, I can figure this out directly. I'm trying to think if I see the value 1 anywhere in this design. I think it doesn't look like that addition is happening anywhere. So I think with the code open, let's go back and take a look at trace our way backwards from there. So all that looks pretty good. How about this one? Internal raw immediates. That looks close-ish, but wrong-ish, I would say. It should just be 1, right, for this instruction. Um, so that is definitely a bug, but whether it's an important bug for us, it's definitely a bug, right? Our 16-bit immediate, this looks like maybe it's the sign extended version of it, so it's the same. Our 16-bit immediate should just be 1 for this instruction. And there's no shortcut to that knowledge, right? That's hard to earn knowledge over the course of this semester. That 16-bit immediate, we're going to sign extend it and all that yada yada yada, but it's just a value of 1 for that instruction. So we should just have 0001 here for that value. So let's see what we can do. Is instruction of 0 to 15. code to 15. We're okay. So this was the code where we're doing that flipping of stuff. So now we're back to here, where there's a little bit flipper module in here. Let's try it with that. So this is going to be fun to debug. I'm seeing this happening a lot, right? And you may be double doing it. You may be flipping and then flipping back. So um, with this team, we discussed whether it was worthwhile to kind of redesign your components or just to kind of try to make it work where you have certain things going upwards and other things going downwards. In this case, we can see what we can get through, but that's an artifact of that. So the instruction was correct. We were grabbing the wrong bits because 0 to 15 wasn't the value we were expecting. It would actually, in that case, have been 31 down to 16 would have been the bits that we would have wanted to grab. Same issue here, but we should be able to uh, track down exactly what's happening more quickly now. I would still argue this is a 5-minute bug. In terms of discovering the bug, we have found it. We may not be able to resolve this in the time we have remaining today, but it's all part of the same issue here, where instruction internal immediate is still wrong. Internal raw immediate. Just trying to fix one thing at a time. I didn't look at how you were doing the code there. So this is how you were flipping them before. So instruction of I is S instruction of 31 minus I. So if you do it that way, then 0 to 15 would still be Christ, this is backwards in my head. I don't know. It's something to do with that. So we got to make sure we're grabbing those right bits from there. We want to grab from the instruction, which is this value you have here. We want to grab, because of how we did that, bits 16 to 31 is what we want to grab. It's a coincidence that the value looks close. It's just a coincidence, right? Because of the instruction itself has a lot of zeros in it because there's destination or source register is 0 and the opcode is 0. It looks like it's close, but it's the wrong 16 bits of the instruction, so it's actually not close. But this is involving a lot of like double negatives in my head. So we have an instruction that is correct. We want bits 15 down to 0. Everything's going to be backwards the way you're doing this, though. So that bug, we are going to we're going to leave that here for today with this bug. I think we can resolve it. That's not going to fix it either. It's going to be the same issue. So bit 0. Let's walk our way through it. We want bit 0 of the S instruction signal is a 1. That's our 32-bit signal coming off the instruction memory. That's going to then correspond to, if we're doing this flipping of the instruction here, that is going to correspond to bit 31 of this value. But all of these are going to be wrong, though. You have to go back. If you're going to do it that way, you have to go back and then grab the other bits in all of these, which would be bit 16 to 31 would be what we would grab. Whereas, I mean, that would be the way to do it. That's going to fix one problem and create several more, though. Let's give it a try. Not give up that quickly. Yes, coincidences are absolutely the worst during debugging because it looks right and it could just coincidentally be right earlier, and then the fact that it's wrong now is actually the correct result, and it's not that easy to find. Yeah, this thing is gonna frustrate me a little bit. My suggestion would again be a refactor in which your components are all running in all the same direction, because This is just one instance of a reverse polarity kind of issue here, and it's just going to keep coming. It's not going to go away just because we resolved this particular one here. Um, so there's our instruction. There's our internal immediate. That looks promising. Um, okay, so one problem solved. We have our, and again, let's make sure we're in the right place. We're right here. Um, we have our read write data is still 0. Where is our actual ALU IB? Now we have to look at that part of the code and figure out where that addition is happening. Next thing would be wrong would presumably be in the code. Um, let's see where this is being used. Okay, that internal immediate. Let's double check that that value is actually correct. That internal immediate. We also can do a, I forget how to do a find signal name in here. It's in there somewhere. I think I can even just do like a control F. Yeah, so internal immediate. It's right there anyway. Um, that value is correct. So we have the right immediate value that we have here. Where are we using that signal in our design? With a mux to determine what that is it immediate value for B, and we already checked that was correct. Good. So we have input A is internal RS, input B is this signal, ALU op. Let's take a look at what our ALU sum result is. And our ALU sum result is 0 here. So the next thing would be, and I would probably, it's all technically here. You can see the values. They're on here somewhere. Input A, heck, let's just add them again. They're already there. Let's add them again. We don't know where they are in this huge stack, but we just added them down here. Internal ALU result looks good to me. That signal is not getting connected to anything. We're running out of time here. I understand. Put A out data. Where's that internal ALU result is correct. That part looked correct. We're getting somewhere. And now when we look at that internal ALU result, what is our actual output is called out data here. But our out data is all zeros because we have a mux in which we have a control for, is it an ALU? That's our big mux at the end of our ALU, right? Is it a shift operation, or do we take the output of the shifter, or do we take the output of the whatever the ALU out is? And my assumption would be input A would correspond to 0 and input B would correspond to 1. But I would say not to trust, but to instead verify. That's using individual. This should be very similar to, it's mapping a component called mux. And yours is backwards, which is fine. So your inputs to your muxes are backwards. Let's confirm that the control signal is what it's expected. Control is 0. So that's taking input B. Your mux is in fact backwards than everyone else's. That's okay. That's life. But that would be my fix for that, right? Would be, if that's the case, at least make sure your inputs to your muxes and your control signals are all in alignment. Whether you want to change your spreadsheet when this is the case, or whether you want to change your mux inputs, doesn't really matter. You just have to agree as a team that that's the correct thing to do. We have time to run this back one more time here. I want to show something working. This has turned into more than a 5-minute bug. I guess roughly they were 20 minutes each. This one's a tricky one though, right? So again, the thought process there is, okay, we're writing to the right register, but the value's wrong. We fixed an issue with the immediate, but the result of the ALU was wrong. And you just have to keep asking those why questions. Why was the result in the ALU wrong? For what it's worth, we got a little further. We got the first instruction did work, but not the second one, which is weird and scary to me. But at least we've gotten past one bug there. That the first instruction is at least working. Now we move on to the next instruction. It's interesting. That's interesting to see because why would one instruction work but not the next one? It's going to be one of those things again. Is it the ALU output? Is it the immediate input to the ALU? Is it some control signals that we have there? That's the process you have to keep following as you go through and as you do this. Let's leave things here for today. We can do more debugging on Friday if you'd like. Otherwise, we should just continue with talking about pipeline processors and understanding hazards and how to detect and how to potentially prevent them in our pipeline. Enjoy working on Project Part B. Let's all get our percentages up to 70 or so as quickly as possible, so that we can take the time and get the last part of it done. Um, Good luck, and I will see everyone on Friday.